Is my screen visible to you?
Yes.
Okay. So the entire confusion we had in this part, right? Let's work in that confusion. Okay. So this cos beta is equal to u this cos beta is equal to u transpose. Are you agree with this?
Yeah.
No, Ashutosh, I have doubt here. So cos beta is equal to this divided by that norm term, right?
Yep. Denominator term, I agree with you. Okay. Since it was
So
positive only,
you can write it as k because you have denoted it as k, so you don't have to write whole thing.
okay. L theta. Actually, I should have written here directly proportional. Instead of this directly proportional sign, I should have written. Okay. Now, what I'm saying this is this k cos beta is equal to ut. Is it okay?
Yeah.
Okay.
Makes sense.
Why this is that's what is not clear now. You're saying cos beta is equal to that, but then you suddenly added k on the left side. But then you should also add. Multiply the right side term with k, right?
Okay. What I'm saying this is okay. You can understand like this. If you will do cross multiply here, it will go here. This is a constant term.
Yeah, it's a constant term.
Can you say that this is equal to k?
Yes.
Right?
Yes.
So in this way, you can understand this k cos beta is equals to ut.
Yeah.
Right?
Okay. So are you saying that normalized value is nothing but k?
This is not
Yes.
normalized. This is this is constant word. Yeah, you can say like that also.
Okay.
Right? So what initially I was doing is I was multiplying k in both the side, right? What was the value of k? That the value of k was equal to denominator. That's why the denominator was getting knocked off. Right?
Okay. Yeah.
So it is just a cross multiplication, right? On both sides.
Yes. You can say consider it as a cross
Yeah,
multiplication
okay.
also.
So if you multiply it, so that denominator will get cancel, and in right hand side and left hand side we will get k. Okay, understood now.
Right.
Yeah, it's clear, Ashutosh, now. So
Yeah.
basically, you have multiplied that
Yeah,
normalized value everywhere, and that's why it has
Yeah.
been knocked off from
Yep.
middle.
Yep. See, what I can do
Yes.
is I can multiply if I'll multiply my, q on both the side. This will become like this. Sorry.
Yeah.
Q. Right.
Q.
Or else I could have said that I am cross multiplying q on both the side. Both the meaning of both the thing is same, right?
Yeah, we understood now. For me at least it is clear now.
Everybody clear?
Yes.
Okay. So what intuition that we are deriving from here, if you want to minimize the loss, you should always move in the opposite direction of your gradient. Okay. If this was the function, this is the loss function, here you are having minimum loss, you should always move in the opposite direction of your gradient, then only you'll be able to approach toward minima. Right? Here the direction.
When you say gradient, what exactly you mean here?
See, this is a function. What is the direction of this function? What is the tangent? It is like this. The gradient is positive, right? If I have to approach toward minima, I need to move in the opposite direction.
Yes.
So I'll approach in this direction.
Yes.
Why I'm moving in opposite direction? Because my angle should be 180 degree.
Yeah.
When my angle is 180 degree, that means what? I should move in the opposite direction. If my angle would have been 0 degree, I should have moved in the same direction of my gradient.
Yep.
So that's why this inference came out of this.
Okay.
Okay. Now let's move to the other slide. Okay. Now, when I say gradient, what I meant? I meant simply the partial derivative of my loss with respect to B and W.
Yeah.
Right?
Yes.
So what was my expression here initially? My expression was W equal to W plus eta delta W, right? Now, one thing I understood is we should move in the opposite direction. That's why I'll have a negative sign here,
Yeah.
right? And what was my delta W? My delta W is what? Delta loss with respect to W. This is the gradient, right? This is the gradient part. So I should always update my W, right, by subtracting it with the gradient of loss. Okay.
Yes.
That's why this update rule came. W t plus 1. That means in t plus 1th iteration, subtract the value of W in tth iteration minus, subtract this one with the gradient of loss with respect to W.
Ashutosh, can you go back to previous slide?
Sure. Any confusion?
No, okay. Yeah.
That's why at the beginning I told that this, if you can understand the value of this delta W as dl by dw, right? So we have seen also now that dw is equal to dl by dw, the gradient. Okay. So are you clear with this update rule?
Yes.
This is nothing but gradient, right? Delta wt is equals to gradient of loss with respect to W and gradient of loss with respect to threshold, that is B.
Yes.
Okay, so this is the entire sigmoid learning algorithm.
But Ashutosh, what I have understood so far was that the sigmoid learning algorithm is nothing but we are applying that function to perceptron algorithm, right?
Yes.
Perceptron learning algorithm.
Yes.
So then it sounds as if that sigmoid learning algorithm doesn't really have any algorithm. It's just that you're applying that function to an already existing algorithm. But then now here you explain this whole thing.
Yes. Yep.
Right. So that's a bit confusing.
Yep.
That what should I understand, that sigmoid algorithm is actually a new algorithm, and where we are
Yep.
totally doing something different than what we did in perceptron.
No. Actually, see, yeah, definitely sigmoid learning algorithm is different than perceptron learning algorithm. You know, that algorithm we have learned in case of perceptron, there we were doing simply addition or subtraction, right?
Yeah.
So there are certain limitations with perceptron learning algorithm. Like for example, you were always doing summation by x or doing subtraction by x. We did not had any mechanism to control the step toward minima, right? So this is altogether different set of algorithms. This same thing could have applied to perceptron also. Getting, this is altogether a different set of algorithm, and this is the most a powerful algorithm we have in entire machine learning. This is called gradient descent.
Yeah, but the way you said that in sigmoid remember that function that you showed, right? That
Yes. Yep.
WTX plus B, we are
Yes.
just applying sigmoid function on it,
Yes.
and we're getting some output between 0 and 1, right?
Yep. Yep.
My understanding is that in sigmoid, there is actually no algorithm going on. It's just some mathematical function is being applied to an existing algorithm.
Yes. Yep.
Is that so?
Yep. That is absolutely correct. Instead of this learning algorithm, we could have simply done the perceptual learning algorithm also here. We could have
Yeah.
done that. But see, in that case, the disadvantage we are having is we do not have any mechanism to control our update, right? Like
Yeah.
here we have defined eta here,
Yeah.
right? So this
Yeah.
is so obviously in that algorithm there was certain flaw. In order to overcome that flaw, people came up with this entire new framework of getting the optimal value of W and B,
Okay.
right? So this entire thing that we have.
So,
Mhm. Yep.
so like in sigmoid algorithm, one function is 1 divided by 1 plus e raised to that wx plus b something.
Yes.
So is it that for updating the value of w and b in that sigmoid function, we are using this parameter update rule,
Yes.
whatever we learned just now.
Yes. Yes. Right. You could have, instead of this thing, you could have simply done something like this also. W plus x, w is equals to w minus x. The thing which we have learned in perceptron also.
Yeah.
You could have done that. But the problem is, see, what happens with this algorithm, I'll tell you, perceptron algorithm, if suppose this is the loss function you're having, right? And this is the point where you want to reach. Now, since we do not have any mechanism to control our change, to control our update, what happens is you have, let's say at this point you are in this particular position, you are doing a constant update. We're constantly updating by either x or subtracting by x, right? So I'm doing update like this, this, and there is there may be a chance that I might overshoot the minimum point,
Yeah.
right? So what people understood is this perceptron algorithm is not really giving us the convergence criteria. Many times they saw that it is overshooting the point of minima and the process is going on for like forever, right? Now think that instead of this a really concave function, if you have function something like this, in this case your perceptron algorithm will fail, right? Because we do not know at what particular direction we should go. So, but in case of sigmoid neuron with this gradient descent, we always know that we should move in the opposite direction of gradient. If I have reached here, I should go in this direction. If I have reached here, I should go in this direction. Right? So,
Yeah.
so this algorithm you can apply in case of perceptron also. But this is a recent update. That perceptron algorithm we learned, it came, I think it was in 1914, people came up with that algorithm. But later, that algorithm was refined, and this is the recent algorithm which we follow in most of the machine learning and deep learning, problems. Understood? Any confusion? Any doubt? Let me know.
Yeah, I mean, I understood the algorithm itself, like the way you've explained it today. My only confusion was earlier in the last class, I think you were saying that sigmoid algorithm is nothing but applying this function to perceptron algorithm.
Yes.
So my understanding till yesterday was that, okay, that
Yeah.
means this algorithm is actually doing nothing new. It is just applying a function.
Yes,
But
it is.
now you explain this whole new way of doing.
Yep. Yeah.
So that means
I would still say that this is similar to perceptron only. It's just that the mechanism we are following to get the update value is different here.
okay.
You,
So if we can pause on this slide, right?
Mhm.
Only I will ask you.
Hmm.
y cap is equal to 1 by 1 plus, e minus, okay. So
Hmm.
WXP is nothing but perceptron algorithm uh, summation, right? Like that's what the model is, WX plus B, right?
Yes,
So,
exactly.
and the loss is, as you correctly mentioned there. Now, if looking at the function, looking at this expression itself, it says that, okay, this is nothing but perceptron, the summation, the whole thing model being a function being applied to it, right? So
Yes.
there's no new step coming in, there's no new logic coming.
Yep.
But then on the left hand side, we are coming with this thing of WB initializing, iterating.
Hmm.
That's what kind of I'm thinking that
Okay.
right side I'm looking, feeling like it's just perceptron with a function applied to it. But
Yes.
then on the left side, it is giving an impression that, oh, it's an altogether a new algorithm.
Yes. Yes. Yep. Yeah. It's not an altogether new algorithm. It's just that a small part of that algorithm is updated now. You see, in case of perceptron, also we initialize the value of W and B
Yeah.
by some random value,
Yeah.
right? We compute the loss in case of perceptron also,
Yes. Yes.
right? And we update, and whenever there is a misclassification, what we do is we update the value of B and W, right? In there we were we were updating W by W plus X or W minus X, right? So just the update part we are changing here. Why we are changing here is because this algorithm has to cater the need of two kind of problem. We are trying to solve a regression also, we are trying to solve classification also here,
Oh, okay. Okay.
right? In case of, see, in case of your perceptron, it was pretty straightforward. It was always 0 or 1.
So what if you had done this iteration of, like the way we are doing in Sigmoid? What if you had directly applied it into perceptron then?
Yeah, you could have applied this to perceptron also. This gradient descent, you can generalize it for perceptron also.
So is it like done? I mean, but why we didn't do it right. You didn't show that. You just showed the way perceptron is, and then you
Yes,
shifted to.
yes. The reason is, see, in case of perceptron, we deal only with categorical output, right? So this
Yeah.
algorithm will be too much of overkill for solving that trivial problem,
Okay.
right? So since with in case of sigmoid neuron, we are trying to solve regression and classification also, right? That is why we made a slight adjustment in the way we do update for the value of W and B.
Okay.
Okay.
Okay. I think now I'm clear.
Okay, great. Thanks, Salman. That was really a good question. It might have helped the other audience also. Okay. So tomorrow, what we're gonna see is, so right now till this point we have agreed that this delta WT is equal to gradient of loss with respect to W, gradient of loss with respect to B. Tomorrow we'll see that how do we compute this gradient value? Okay. How do we take the derivative of loss with respect to W and derivative of loss with respect to B? Okay, so this is, so for tomorrow, it would be really helpful if you could do some revisions on your derivative concept, how the chain rule applies in case of derivatives, how do we differentiate, some primitive, some small functions. Okay? And after that, we will implement this entire thing in Python. Okay. Okay, if there's no further questions, we can call for the day. We'll meet tomorrow.
All right. Bye.
Okay. Yeah. Bye bye. Thanks, everyone.